Typically this would be done with, well, geometry, but again, I'm supposed to prove it in dumb ways. So instead, I'm actually going to look at the power series of sine and cosine. So sine of x has a power series of sine has this power series, where sine alternates and we have odd powers and odd factorials. And cosine is the same, except it's now even powers and even factorials. So how do we go from this to this? And for that, I'd like to, instead of deriving the formula for the angle addition, let's derive separately these product formulas. Let me number this 1, 2, and we have some formulas we want to prove A to D. So these are the product identities for multiplying sine and cosines together, and it's not that difficult to see that, say, adding A and B together would give us sine of x plus y, which is exactly formula 1, and likewise subtracting D from C would give us formula 2. So proving these is equivalent to proving this. Well, how do we prove these then? Cauchy products. So, short explanation of Cauchy products. I'll probably have a video in more detail about this sometime later, but for now, Cauchy products are a way to multiply two infinite series together. So the idea is this. Well, we just distribute every term into this infinite series and just pick out all of the products in a way that if I create another infinite series that is the result of this product, and I name this the C0 coefficient, I take all the products such that the indices of A and B sum to 0. Then I take for C1 the products A and B such that their indices sum to 1. And then I just repeat. So this creates this infinite series with coefficient Cn, where it's this sum. As in A, the index of A starts from 0 and goes to n, where n, the index of B starts at n and decreases by 1 to 0, which is exactly what we wrote here. In other words, multiplying these two infinite series of coefficients A and Bn gives this one kind of like double sum. It's a new infinite series as n goes from 0 to infinity, and we just put in the definition of Cn here. So using this, we can now compute the products of, say, sine and cosine and see what we get. Say I multiplied cosine x times cosine y, product of these two infinite series. This is an, and this is bn. As n goes from 0 to infinity, of a sum that goes to n from k equals 0 of ak. So let's just put this here, just replacing n with k, and bn minus k, replace n with n minus k. Let's now see what cancels or what we can take out of the sum. So we got minus 1 to the k and minus 1 to the minus k. These cancel, and minus 1 to the n we can take out of the sum. And we can also take y to the 2n out of the sum. And x and y would be, I'll write it like this, x over y to the 2k. And now, if you can see here, we're actually very close to having a binomial coefficient here. So what we do is add an extra 2n factorial term here and divide it out here. So now this is 2n choose 2k. Also, I'm gonna denote x over y as z. Okay, at this point, when I first tried this, I was just kind of stuck and wasn't really sure what to do. But knowing how this worked out for the exponential function, and that we have now binomial coefficients and, well, an increment power, And we know that 1 plus x to the n can be written as such sum of binomial coefficients and an incrementing x power. We'd like to somehow express this sum as this instead. And for that, we kind of do need to do a little trickery. Because you see, this sum, maybe you'll see the trick if I write out all of the terms without sum notation. So, if we replace n with 2n here, 1 plus z to the 2n power, and if I write this sum down, it would be... Now, here's the thing. All of these terms are a part of this sum, as in this appears here, this appears here, as in all even terms of this sum is this sum, but how do we get the even terms from this? Aha, now here's the trick. We take 1 minus z to the 2n, which replacing z with minus z, we have minus 1 to the k, so this would be the same sum, just with alternating signs. It ends on a positive sign because 2n is even. Now, this, and added this, all the odd terms would cancel out, and we have 2 of each even term, which is exactly what we want. Well, 2 times this. So what we have is that this sum that we want is 1/2 of 1 plus z to the 2n plus 1 minus z to the 2n. And this trick will pretty much just finish the rest of the proof for us. So, taking this expression and putting this here, we have that cosine x times cosine y gives 2 sums. And another sum, just the same thing except minus here. And now since y and this thing in the parentheses both have the same power, I can distribute y here and y here and get 2 sums. This one would be, well, y plus x or x plus y, yours doesn't matter here. And another sum that has y minus x, but since this is an even power, I can also just change the order. And these are now by definition 1/2 cosine of x plus y and 1/2 of cosine of x minus y. And I guess I could say we're done, since well, I should also derive all the sine x times sine y, sine x times cosine y, but they actually all have just the exact same trick. Just for some of them you choose the power here to be 2n plus 1, or you subtract instead of add these two, but it's actually just the same trick and it's very straightforward, so I don't see a reason for me to do so. And as I already shown before, this implies the addition identities. So that would be it for this video. I hope you enjoyed. I'm gonna do more of these, what do they even call it? Basic proofs, no, basic facts dumb proofs. Prove more simple theorems and identities using some overpowered techniques, I guess you could say. Oh yeah, by the way, I have a gaming channel. Yeah, mathematicians also play games, right? Yeah, I'm an epic gamer.